Hello students, this is the second class of dimensional analysis. If you missed the first class, then please go through the first class, then you come to the second class. So the link will be in the description also, and in my channel also you'll get the link of the first class. Okay, so we learned Buckingham Pi Theorem, dimensional analysis on differential equations, and dimensional analysis on integration. This class is mostly for BSc and MSc guys, so IIT JAM and CSI NET aspirant, please follow. We start with Buckingham Pi Theorem. This is very interesting. If we have n number of quantities with d independent dimensions, then we can form n minus d independent dimensionless quantities. How we understand it? Let's consider the pendulum example once again. We have four quantities here: mass of the bob, length of the thread, acceleration of gravity, and frequency of oscillation. And their dimensions we already know. So we have four quantities and we have three independent dimensions. We only deal with m, l, and t here. No other dimension, fundamental dimensions appear there. So we have four quantities and three independent dimensions. So we'll get 4 minus 3, n is 4, d is 3, equals to 1. So we'll get one independent dimensionless quantity. So it's a singular number, So, and that quantity we already calculated in class 1, that is v square L by g. This is a very simple application, but Buckingham Pi Theorem deals with more complicated problems where we deal with many more quantities. Okay, let's go through. Okay, let's say in the pendulum once again, we deal with, we add one more quantity, which is, say, amplitude of oscillation. So what is the maximum theta your pendulum can have? So this is amplitude. This amplitude does not have any dimension. Theta is dimensionless. So now let's say the time period of frequency may depend on the amplitude of oscillation also. So here we have 5 quantities and we have 3 independent dimensions. So here we must have 2 independent dimensionless quantities. One is theta itself, as we already know. So theta is dimensionless and any function of theta is dimensionless. And another quantity is v square L by g. So you have 2 dimensionless quantities here when you are dealing with 5 quantities with 3 independent dimensions. Okay, so this I have already told you. So okay, so this is dimensionless. So what can we say about frequency? So if this is dimensionless, and nu square L by g will be some function of theta. So we can say it a function f theta. So this f and this f are different. So let's say we call it, say, f1 theta. Not a problem. The main application will be in some more complicated problems. Let's say you are throwing a paper helicopter. Paper helicopter we play with in our childhood. We play with some paper helicopter. We made a helicopter with paper. So let's say with a paper helicopter with radius r and weight w is dropped from a height h in air. The density of air is rho. Let's assume that helicopter quickly reaches its terminal velocity, that a fixed velocity, then it goes down. So can we use dimensional analysis to analyze the total flight time t? Here we don't get an exact expression, but we can extract some information from here. And we'll see how Buckingham Pi Theorem applies there. So okay, so what are the quantities we are dealing with? One is the flight time of the helicopter. Second is the helicopter radius. Okay. Okay, you don't have a proper rotor in a paper helicopter. We made it childhood. So let's say we are dealing with some radius of the helicopter, some length of the helicopter. Okay. Then we are dealing with the height. We are dropping from a height. That height will be something to be considered. That height have dimension L, the radius of the helicopter have dimension L, the flight time have dimension t. the air density, any density have dimension m L to the power minus 3, and weight of the helicopter is just force, so it's mlt minus 2. So we have 5 parameters and we have 3 independent dimensions, m, l and t. So we must have 2 independent dimensionless quantities here. Here we have grammatical mistakes. Okay, so we must have 2 independent dimensionless quantities in this problem. One can be easily seen that r by h or h by r is dimensionless. Of course, the radius and height both have dimension L. So r by h is dimensionless. So any function of r by h will also be dimensionless. This is to be noted with right now. And let's say we start our analysis by saying your flight time depends on the radius of the rotor to the power a, height to the power b, air density to the power c, and weight to the power d. We have 5 quantities. So let's say we already form one dimensionless quantity, another will be formed in this analysis. So we are directly saying that flight time is, let's say, proportional to this. So just equate the dimensions here. So t at left hand side, this is only dimension of t. And then L to the power a, L to the power b, rotor radius and height both have dimension of L. And air density and weight, A, B, C, D, we take it. And we just do a routine dimensional analysis, equate the power, extract all the powers of L or powers of M and powers of T, and equate with the left hand side. What do we get? We get D equals to minus half from here, and from the dimension of M we get C equals to half, but we cannot get A and B exact analytical value from dimension of L. We can only get A plus B minus 3C plus D will be 0 because we don't have L at the left hand side. So just using these two values, but we get A plus B minus 2 equals to 0. So only one information we can have by dimension analysis up to this is your A plus B will be 2. But still we got some information. Dimension analysis cannot give you all information every time. In the first class, we have exactly determined the dependency of many quantities using dimensional analysis. But that does not mean that every problem you analyze, you get a very good result. So this paper helicopter problem is an example that we cannot get very, very far, but still we can get some information. So the first information is this D and C we got exact. So that is dependence on air density and weight. And we can easily say that your flight time of your helicopter directly proportional to rho by W. So if your air density becomes doubled, keeping all the other factors same, so your flight time will be multiplied by approximately 1.4. And this is similarly applied to the weight also. So we write it right now that your flight time is proportional to or equals to, with some constant k, that r to the power b, h to the power b, r to the power a, h to the power b, some function of r by h. Why this is to be introduced here? Because we already know that r by h is dimensionless, and if something dimensionless you have already got, as we see in the pendulum problem, if something you already got, you must include this somewhere at your final result. You can do it in LHS or RHS because you don't know the form. We need to do some physics, apply some physics later, but dimension analysis tells you that if you get some dimensionless quantities, you just add it somewhere, either in LHS or in RHS. So this function will include. This is our algorithm. And then this we already got, C and D. And r to the power a, h to the power b, I will write it just like this, with a note that your a plus b should be equals to 2. a plus b should be equals to 2. So if you divide this right hand side expression by t, so you get a dimensionless quantity. That will be your second dimensionless quantity. I will write it. So let's write it once again. So the same thing I write it here with a note that a plus b equals to 2. So your flight time you can write could be proportional to h square f some function of r by h square root of rho by w, or you can write it r square, or we can write it rh also, or any combination such that your a plus b equals to 2. So that is not a very good answer. This brings you to many possibilities. So you cannot get it exact, but you can get this exact. So dimensional analysis can give you the dependence exactly on air density and weight, but cannot give you dependence on rotor radius and height h. Dimensional analysis itself cannot do. So these will be your possible answers, and there are many more possible answers also. And if you bring this t at RHS, so the dimension of LHS and RHS are same. So if you divide this RHS by t, so this quantity with condition a plus b equals to 2 is your second dimensionless quantity. That is not very tough to understand. So Buckingham Pi Theorem applies here. We got two quantities. One is r by h, and another is this two-dimensionless quantity, as we had five quantities to consider with, and only 3 dimension ml and t involved. That theorem is actually applied to much more complicated problems and many manipulations. So but that you don't need to go through. But if you do some research at some point of time on scaling and dimensionless analysis itself, you will see many problems which have some applications of this theorem. Okay, so let's proceed to the second part, that is dimensional analysis on differential equations. We start with very simple things. So this is the wave equation. You already know it. Del square u del t square is c square, del square u by del x square. You can be anything. You can be anything. I'm not bothering about you. I'm just asking you what is the dimension of c in this equation. It should be very simple. That if you consider your left-hand side, the dimension is the dimension of u by dimension of t square, because double derivative, you're taking derivative twice. So this dimension is ut minus 2. And dimension of RHS is dimension of u, dimension of c square, and dimension of L square, because by dimension of L square, so it is L to the power minus 2, as you are taking derivative with respect to x. So just now, the only thing you consider is that your dimension of LHS and RHS should be same. So that directly give you the dimension of c square is L square t minus 2, and the dimension of c is L t minus 1. So c is nothing but velocity. Nothing but velocity. If some point of time, if any point of time, if you forget that c square is it here or here, c square multiplied with del square u del x square, or c square is multiplied with del square u del t square, you just do a simple dimensional consideration, you'll get the result. So I hope this thing is very clear. But now we will deal with something more important and something more interesting. Consider Schrödinger equation. Schrödinger equation of electron in hydrogen atom. So the equation is this. I'm writing it in three-dimensional form. So it's a Laplacian. It's h bar square by 2m minus the Coulomb potential multiplied by psi is E psi. Suppose you just have this equation. You don't know anything else. Just looking at that equation, and without solving that equation, can you have a rough estimate of size of the hydrogen atom? This is an equation electron will follow, and electron, elementary idea, you can say that electron have a circular type of path because of this potential. So what could be an elementary estimate of that electron radius? Can you do it, but just by looking at the equation itself? Our dimension analysis says that we can do, and physicists do it every time. Every time they apply a new type of equation to a new type of problem, they do some dimensional estimate. Then they go to the proper solution, either by analytical consideration or by numerical consideration. So our goal is to have an estimate of radius of hydrogen atom. That means full solution. To estimate the energy of hydrogen atom, all this. So how do you do it? We have few constants there. One is h bar, another is mass of the electron, charge of the electron, epsilon naught. So these values we know. In a problem, let's say it's an unknown problem, something of radius is to be considered, something of dimension of length is to be considered, and that problem involves h bar, mass, charge, and epsilon naught. So let's say e square by 4 pi epsilon naught. Let's group it. Let's group it and see this is a common variable, e square, common constant. So that should be written as group constant, that is not a variable. So grouped constant. Can I shift it a bit? Yeah. So this is e square by 4 pi epsilon naught. Let's call it k. This is Coulombic k, m and h bar. And dimensions of these are this. We have already calculated it in the first class, so don't miss the first class. So it's a energy from E equals to h nu. You get the dimension of h bar. Just from Coulomb's law, you get dimension of e square by 4 pi epsilon naught. So we have three quantities with dimensions known. So my question is, can you form something of length L using these three quantities? That seems trivial right now. Sure. If you just divide h square by mk, divide by mk, so you can easily see the length is L. H bar is ml square t minus 1, so it's m square L to the power 4 actually. So I missed this. Okay. So m square L to the power 4 t to the power minus 2, and below we have m and k. So this m square cancels, so you get L. Tt cancels. So h square by mk is the quantity which with dimension of L. So your Coulombic in the Coulombic potential, your electron radius should be around the numerical value of this. If you substitute your k is I defined as k like e square by 4 pi epsilon naught. So if you substitute the value of k, you get this. And if you substitute the numerical values of these constants, you get 10 to the power minus 10 meter. 10 to the power 10 meter. This is order of Armstrong, and this is very close to your, perfectly matches the order of your exact value. So it is not a surprise that these constants will, after combination, will get you a value of this. So without even solving the Schrödinger equation, just by looking at that equation, just by knowing that your electron radius should depend on this constant only because we don't have any other things in the equation, you can have an estimation of that, estimation of the value. Superb, right? That's the thing I wanted to tell you. Now, we have three constants. Can you make something of dimension of energy? Sure, why not? In the dimension of energy, I know ml square t minus 2. We have three constants here. So we can make a combination. Mk, you do it yourself, right? This is just a trivial algebra. So mk square by h bar square, just a simple algebra, give you this quantity is of dimension of energy. Simple. So what will be the numerical value of this? Very interesting. mk square by h bar square, properly written, will be this. And if you just put the values, this gives you 27.2 electron volt. And that is exactly double, just double. That's not correct within a factor, of course. Just double of what you get by solving it. Properly solving, you get 13.6 electron volt. And just a dimensional consideration give you 27.2 electron volt. So whenever you have this equation, you know that you're looking to find some radius with an order of 10 to the power minus 10 meter. You are looking to find some energy near accurate to factor of 10 within 27.2 electron volt. That is amazing. I found it amazing when I first learned it. Not very long ago, I learned all those things. So I just learned, say, within a span of 6-7 years. Not in my BSc and MSc, I knew all of this, that by dimensional considerations, we can reach this far. I didn't know in my BSc, MSc time. Okay. So let's proceed. Can you make something of dimension of velocity using them? Sure, why not? If you just divide your k by h bar, the dimension matches with L by T. So that means the velocity of your electron in that Coulombic potential should be equal to order of k by h bar. And that is just C by 137. That 137 I will tell you. I'm just going to tell you the significance of that. This is E square by 4 pi epsilon naught h bar. The numerical value of it just around 2.2 into 10 to the power 6 meter per second SI unit. So very high speed. Electron will have very high speed. You already know that. So this is just dimensional consideration giving you. Now, what is this? 137. How do I write it 137? Okay. So we have three quantities in Coulombic potential, Schrödinger equation, m, h bar and k. And you already seen that the velocity of electron will be high. See, I'm using 137 just I know. Otherwise, you just put the values and get this. So you're seeing that you're dealing with high velocity electron. So special relativistic effect may be important, might be important, considering this problem. So, but I'm not going to relativistic dealing of this. There could be an interesting study of this. I already seen it in many books. So if you are interested, you can have a Google search and go. But my question right now for you is, I need to put a comma here. Not okay. So as we already know the relativistic effect might be important, so can you make something dimensionless using your mass of electron, h bar, that Coulombic k, and velocity of light? Because why I am asking for a dimensionless quantity? Because this dimensionless quantity could be very important, because all these are very fundamental constants of nature. So just involving relativistic effects also, if we can form something dimensionless, so that quantity could be very important in all relativistic dynamics of electron inside electromagnetic field. This is an entire generalization. So you know your electron, you know your Schrödinger equation, you know that special relativistic effect could be important. So without going to relativistic quantum mechanics, without solving that Dirac equation, Klein-Gordon coefficient, without knowing all this, I just want to know is there something dimensionless can be formed using these four constants? You readily see that you can do. And what it will be? K by h bar by c. This will not have any dimension. K by h bar has already have dimension of c, already have dimension of velocity. So just divide by c. You get a dimensionless quantity. E square by 4 pi epsilon naught h bar c. If you calculate, you do this, right? Everything I tell you, you don't just take it for granted. So if you calculate this numerically, you get the value 1 by 137. And as your physics study will continue, you'll see this 1 by 137 is a very, very important parameter. Very, very important. Even it extends to the ratio of strong force and electromagnetic force. This is sometimes called coupling constant. Very much important in quantum electrodynamics, relativistic quantum mechanics, quantum chromodynamics, all the particle physics auxiliary. This is so important. So you can, without knowing all this, we just have an elementary estimation that, okay, this 1 by 137 may come to nature. Nature may have some secrets building around this thing. Whatever system of units you take it, your ratio of these quantities will always be 1 by 137, independent of the units. That's why it's dimensionless, right? So it is in generally called fine structure constant. Okay, guys, interesting things. Next part. When we need to solve an equation, we needed to write a dimensionless form many times. Because if you do it analytical calculation, you don't need to do a dimensionless form. You just keep all this constant there and just do your calculation, get your result, and write your result, substitute the value of constants and write your result. But in most of the time, the complicated equations are solved numerically. When you solve something numerically, the values of this 10 to the minus 34 and etc., you cannot take these constants in your calculation at every step. So many times you need to write an equation in a dimensionless form first. If you need to calculate this Schrödinger equation, solving Schrödinger equation in using Python or any other thing, this means a numerical calculation, if you want to do on it, you need to write in dimensionless form. So how do I write it? This is an interesting exercise. Okay, this is not tough but slightly time consuming. Okay, let's see how much time we have. I'm already at 28 minutes. Okay, we'll do it quickly. So your dimension of h bar square by mk is L, you already know. So let's define your h bar square 4 pi epsilon naught by me square is a0. This is the Bohr radius. I know the numerical value of it. So it's 0.5 Armstrong around. So let's define it a0 and let's define your r as r by a0. Why am I doing it? This is of dimension of L. So if you define your r prime as r by a0, so your r prime would be dimensionless and your result will be just a number. If you when get you after calculating, when you get r prime, it will be just a number, and that number will give you the result in terms of a0. Just multiply the value of a0, you'll get the result. So right now it may be confusing, so but when you do, you'll get this. Now we need to change the variable. This delta square, this have del square del r square. So how do I change it? We have del r. We can just, this is just chain rule of derivatives. del r will be del r prime by del r into del r prime. So it will be 1 by a0 del r prime. You know the relation. You'll use it. So, okay. So here you already used it. If you take double derivative, you easily can verify. You may pause the video right now. You just verified that del square del r square is 1 by a0 square del square del r prime square. By this way, we are transforming your Laplacian from dependence of r to r prime. Theta phi I am not considering because this is independent of r. Theta will be theta and phi will be phi. So if we just change it, you please verify it by expanding the full Laplacian. So this equation, we can change it to this. Delta square Laplacian square is 1 by a0 square delta prime square. Simple chain rule. We have already substituted your r with our a0 r prime. So I substitute your del square by del prime square. That means in my whole equation we don't have r. We have written everything in terms of r prime. Just a simple algebra. You do all steps, all algebraic steps yourself, right? Just don't skip. Okay, Sir told you, you just accept it. Just don't do that. So you multiply with a0. Okay, that a0 comes here. You substitute the value of a0, which you defined it at your very first step. So substitute a0 here, and then you get this type of expression. You see e square by 4 pi epsilon naught is a common term. So we don't have a0 here. Right hand side we have a0. So this thing we have, you do a simple algebra, h bar square by h bar square by 2m. That h bar square by m, this cancels. So e square by 4 pi epsilon naught as a common term. So you take this term at right hand side. So your equation becomes like this. We are almost done. Delta prime square psi minus psi by r prime is a naught e 4 pi epsilon naught by e square into psi. So this is, you might see that I am here. So this step, okay, this is, what should I say it? So this thing is just ground state energy of hydrogen atom. You defined it. So I put a shape there. Okay. So this is just a ground state energy of hydrogen atom with value of minus 13.6. I defined it. Seeing all this thing here, I defined e square by 8 pi epsilon naught into a naught. That thing, and if you substitute the value of a naught, you get this. So this is ground state of hydrogen atom energy. So now it will be easy to define E prime. This is kind of dimensionless energy. This have dimension of energy. So define E prime is E by E naught. So you get a dimensionless quantity. So just do it. Do this algebras, right? I don't tell you every steps, but I have written almost all the steps here. So you just do this and multiply by 2, you get your final result. That is Laplacian square psi minus 2 psi by r prime is E prime psi. In this equation, you don't see any other constants. You just have r prime, and you know E prime is E by E naught. So whatever r prime and whatever E prime you get, you're getting this as factor of your A0 and your E0. Suppose you get your R as 1.5, your R prime as 1.5. That means it's 1.5 times of your bore radius. And if you're getting E prime as 1, so that means you are getting exactly minus 13.6. If it's get 2, you get 2 times of this 13.6. So that is the beauty of this. Now you can proceed numerically. Sometimes you need to solve, in most of the time actually we solve the radial equation only. So we apply the same procedure here. In the radial equation, the equation looks like the same. It's an one-dimensional equivalent. So we have an extra L into L plus 1, but we don't have Laplacian, we just have d square, dr square. So I give you this as an exercise, although I have written all the steps here, that you substitute your psi as ur by r. That means r psi is u. So your equation will look like this. This is the first thing you need to do. If you have not done radial equation in your life ever, don't worry about it. Just take it granted that we have to solve this equation and you have to replace your psi by this variable. Then you just do the algebra and calculus, of course. You do the calculation and come here, you get this. After that, it's a simple thing. We just replace the same thing what we have just done, r with r prime a naught, then do some algebra, multiply with a naught square, blah blah blah. We know these things we need to substitute. R prime, what is R prime, what is a0, what is e0, and what is e prime. You all know this. So just follow the steps and do the calculation yourselves. You after multiplying by a0 square, I will put the value of a0. You can do it in your way, in your own way. You do some algebra, and you get this. So this is your e prime, and this is your simple. Without any dimension, we have it. So we just do from here. We just substitute your e prime here. So this is the final call. This is the final goal. So you have already did it here. This is just doing this is same as doing this. I just done another calculation with the radial equation only. So the same thing, but okay, we are making it complete. So here I finished the second part of the lecture. Now I will proceed to the third part, which is dimensional analysis on integrations. This is both easy and tough together. What is an integration? Integration is a summation. Fx dx is nothing but sum of a bit of delta x multiplied by the value of f at many points and do a sum. So your integration must have dimension of fx multiplied by dimension of x. I should have written inside the third bracket. So that's it. So dimension of integration fx dx is dimension of f multiplied by dimension of x. Now, suppose you know the dimension of x. No issues. Your fx is defined as a e to the power minus lambda x. Okay, so lambda, we already know that anything inside exponent should have dimension 0, that means dimensionless. So lambda x should be dimensionless. So whenever you know the dimension of x, you see the dimension of lambda is 1 by dimension of x here. Suppose I tell you that the result of your f square x dx is 1. This is given. Suppose I tell you this. So I just get a text box here. I'm telling you this. This is not that this will always happen. If I tell you this, then what can be said about dimension of A? Dimension of lambda is very obvious here. What will be the dimension of A? This is also very easy, not tough. So if your fx is a e to the power minus lambda x, your e to the power lambda x cannot have any dimension, so dimension of lambda is 1 by x, not a problem. And if your f square x dx is 1, right hand side you don't have dimension, so your dimension of f square dx overall should be dimensionless, because right hand side you just have a constant. And what is the dimension of f square dx integration? It have the dimension of f square and dimension of x, that x coming from dx. I already told you. The dimension of fx dx is dimension of f and dimension of x. So dimension of f square dx is dimension of f square and dimension of x. The dimension of f square will be dimension of 1 by x. And what is f square? F square dimension is the dimension of a square, because e to the power minus lambda x cannot have dimension. So dimension of f square is a square, and dimension of f square is already 1 by x. So your dimension of a square is 1 by x. I can put it in this slide itself. So this is simple, not a problem. Okay guys, these are easy things. If you didn't understand, please go through once again, but I need to complete it in time. Now we are evaluating integrals by dimensional analysis. Okay, let's see how dimensional analysis helps us in evaluating integrations. Okay, let's start with a simple problem. Say e to the power minus x square integration over minus infinity to infinity is square root of pi. Let's say you already know this. E to the power minus x square don't have any dimension, so x square should not have any dimension. X should not also have any dimension in this problem. E to the power minus x square, no dimension, and dx, if it would have dimension, right hand side should have dimension of x, but right hand side is dimensionless, so x is dimensionless from this argument also. In another way, x squared does not have any dimension, so x will also not have any dimension, not a problem. So this is not an issue. Now if I ask you that if you know this result, can you predict this result by using dimensional consideration? That's your problem. You know this. Do you know this? Just using knowledge of this black box and dimensional analysis, can you predict the result of this yellow box? I think we can. Let's see. So first thing first, e to the power minus ax square cannot have any dimension because it is inside exponent. So your dimension of a, and this is also a typo, so your dimension of a should be same as dimension of 1 by x square. No way, you must have this, otherwise ax square will have dimension. So dimension of a is equals to dimension of 1 by x square, and dimension of x should be equals to 1 by dimension of a, square root of dimension of a. So that should be written as this. Now consider at the equation once again, that e to the power minus ax square dx, it must also have dimension of x. Here dimension of x is not 0, means x is not dimensionless. Ax square is dimensionless. So e to the power minus ax square dx will have dimension of x. And what is the dimension of x? 1 by square root of a. So e to the power minus x square dx must also have dimension of 1 by square root of dimension a. Square root of dimension a. So how does help calculating the result? Yes, it helps. So e to the power minus ax square dx should be, if this should be equals to 1 by square root of a dimensionally, so the value of this will be some numerical constant multiplied by 1 by square root of a. Otherwise, how can it have dimension of 1 by square root of a? It cannot have until and unless the result depend on some constant, some numerical constant multiplied by 1 by square root of a, because we have only one quantity of relevant, which is a. We don't have any other quantity here. And a dimension of x and dimension of a are related. So right hand side, if have dimension of x, that means it should have dimension of 1 by square root of a, as dimension of a and x are related. So then we must have this. We don't have any other way. And now we apply that. We already know e to the power minus x squared. That means when a equals to 1, you have this. So just to evaluating this constant, I use this result. So now let's substitute a equals to 1. Here and here we can substitute a equals to 1. So e to the power minus ax squared dx should be the constant into 1 by 1. And that result was square root of pi. So now I know that that constant is root pi. We must reproduce this value for a equals to 1. So substitute a equals to 1. You should get this. That give you your constant equals to square root of pi. So then your final result will be square root of pi by a. Not a big deal, guys. I have seen this example in some +2 advanced JEE advanced book also. Just this example. So they may ask, and I have seen one problem involving these integrations in JEE advanced problem really appeared. Okay, but otherwise this kind of problem is basically for advanced guys, for us, for CSI guys. Okay, so let's go to the final part, that sometimes we need to make our integrals dimensionless to extract some physical information. Sometimes we may not do explicitly solve the integrals, but just make it dimensionless and extract the relevant quantities outside of the integration. What is it? Let's say this is left hand side is some time delta t. This is simple integration of conservative system. You will learn it at Newtonian mechanics as more we progress towards Newtonian mechanics. So your delta t is your time required to go from, say, 0 to some constant xc. xc is called a turning point, classical turning point. So don't worry about it. You can get this equation by just integrating your conservative system energy. So we'll do it, but for the time being, say if we need to calculate this integration, that you need to evaluate time delta t, time required to go from some point 0 to some xc point. We need to integrate over the space dx over a line, and what you need to integrate, ke minus kx to the power n with a square root. Here we have square root of m by 2. E is a constant, it's a constant energy, and your xc, that turning point, the value of it is e by k to the power 1 by n. We'll use this value later. Right now we just write xc. So just now think very numerically that you need to evaluate this integration. You know your e is a constant. You know your integration limit ends at xc, and xc is e by k to the power 1 by n. How does this integration depends on e? Can you say it without solving that integration? Think about it for some 30 seconds. That if you are telling this integration is to be evaluated, and the result delta t will surely have some dependence on e, and can we extract that information, that how this integral depends on e, without solving that integration? We can. We have some terms here, because this integration x will not be there, x will be integrated, but e will be there. So if I can get out this e toward left hand side, I might get something. Okay, just take one e outside. So this will be d, take out of the integral this e, take this e here as a square root, and we get 1 minus kx to the power n by e. Now we change a variable. We have this. We put this kx to the power n by e. This is standard technique. Go through once at least in your lifetime. You will need it in your all competitive exam, which is relevant to physics. So this is your kx to the power n by e. The whole thing you put as z to the power n. So that your x is z multiplied by e into k to the power 1 by n. This you can use. X is linearly dependent on z, but with this constant. E is a constant. K is also a constant. These are not a variable. So now you see, if we put this value of x here, so your dx will be dz into e by k to the power 1 by n. So your m by 2 square root of 2e we already have. So your dx change into dz. E by k to the power 1 by n goes out. This is just a dz square root of 1 minus z to the power n. And integration limit goes to 0 to zc, not xc. You change your variable. And your zc is nothing but xc, as your variable changes like this. Your zc is nothing but xc multiplied by k by e to the power 1 by n. And what is this? You got your value of xc, right? E by k to the power 1 by n. So xc into k by e to the power 1 by n, just make it 1. zc was this. xc was defined this. So zc you 1. So this integration, finally, we already got this. We already got your desired result. But still, that zc is also 1, you need to see. So you can already see that this entire integration have just a numerical value. So you can get it, say 0.2, 0.5, 5.2, 1300, minus 1300, minus 1 by 60, whatever. But whatever you get a numerical value. All the dependence of e has been extracted at left hand side. So this integration is completely dimensionless. Numerical factor is there. So now you can see that your time required depends on e to the power 1 by n minus e to the power half. E to the power 1 by n minus half. And there will be a k also. So this is of our interest. This is of our interest. This is a constant. This have a numerical value. This result we wanted, the delta t. How delta t depends on e? Delta t depends on e to the power 1 by n minus half. You will see there are many questions in CSIR NET exam itself that depends on this result, both in classical mechanics and quantum mechanics. And many times you will perform the integration just like this. Believe me, it's my experience. So remember this. If you need to calculate time period of some conservative system one-dimensionally, so your delta t depends on this. Your potential was v equals to k x to the power n. We will just repeat it in our due course. There will be another example. This is from statistical mechanics. Say sometimes we need to perform the Sommerfeld integrals like this. N by v is 1 by 2 pi square into 2m by h bar square to the power 3 by 2, 0 to infinity integration dE over e to the power half e to the, sorry, this is energy E, and this is exponential E by kBt plus 1. So capital E is the integration variable here. So no capital E dependence are there, but there will be a temperature dependence. Here E, energy is itself the variable, but there is temperature dependence. So how does that integral varies with t? I guess you already can guess that. Okay, we will do in this way how we did in the earlier example. Okay, the same thing. You need to replace some value. What do you replace? E by kBt you replace. You just put your E by kBt as x. You just put this. So your dE will be kBt into dx, and e to the power half will be x to the power half, kBt to the power half. So that is easy. E to the power half, there will be a kBt to the power half from here, and from dE there will be another kBt. So kBt 3 by 2 will come outside from this and from this. So kBt to the power 3 by 2 comes outside, and the integration limit does not change. Whatever your temperature is, if capital E is going to infinity, your x is also going to infinity. So then the integration limit remains same, and the integration will be x to the power half dx e to the power x plus 1. So this integration is in dimensionless form, and this integration will have some numerical values. Anything, not infinity, but anything. Say minus 10,000 to plus 10,000, it will have some numerical values, some number. So that give you your expression, that your n by v, what you intended to calculate, and intended to find how this integral depends on the temperature. You got your answer, that your integration depends on t to the power 3 by 2. You don't need to find exact numerical values most of the time in physics. We just need the dependency. Whatever the value is, you got your result. That value can be determined experimentally or some other considerations, or by doing a numerical integrations. We can do it. That is not a problem. So that's it. That's it, guys. That's it for today. N by v depends on t to the power 3 by 2. So thank you so much for attending this lecture. This lecture might have been a little bit tough for you. Okay, you can watch it in multiple times, and you do all the algebras what I have shown you by yourself. Just doing it does not mean anything. Just watching the lecture. You do the exercises, go through all the notes. The notes as a PDF file will be available at the description. So do that, then you learn. So okay, thank you so much. Thank you so much. Next class will be next weekend, I guess, Saturdays. Maybe on error analysis, or maybe I directly start Newton's law of motions and etc. Okay, let's see. Thank you so much.